Hello, this is Daryl Korn, and I am not sure if I need to record a walkthrough for part one of the final project, but it's a habit at this point, so let's do it. And as always, we're going to start with the code. This is my Jupyter notebook for running all of my tests. So starting by looking at the Y label counts here, generating the t-SNE plot here, which is included in my presentation. Here I'm using select percentile to reduce the features and output this graph, which was in the textbook. Here I'm running tests on PCA using cross-fold validation to select 80 and 90% thresholds, which I can explain more in the presentation as well. And then here I'm running my actual tests. So I'm creating my pipeline with feature selection, scaling, and PCA before I try it on a algorithm here. And here's my parameter grid where I search over different hyperparameters and my list of different scoring metrics here. So we run that grid search 4 times. And then here I check the scores for each of the metrics. So we can see here that the train and validation accuracy for the grid search is the best validation accuracy that was in there. And it was with these parameter combinations. Here is the best validation AUC, sorry, with those parameter combinations, and same for F1 down here. And then we can look at the results table if we desire of all the different tests. Okay. To the presentation then. So it felt right to start with an exploratory analysis just to get a sense of what this data looks like. I got caught in the X column in one of my projects, which led to really funky scores, so trying to not do that again. This table here, figure 2.1, is the value counts for each of the Y labels, and we can see that our classes are a bit imbalanced, so we definitely don't want to go solely on accuracy. You can see here that class 1 has almost double the samples than class 2. So we want to look at F1 scores, for instance, to get a better sense of how our model is doing. I also created a t-SNE plot here just to kind of get a sense of how separated all these classes are, how distinct they are. And we can see that I think we can pick out fairly good distinctions between the classes. So there is a bit of overlap, which may show that the classifiers may struggle on a couple samples. So class 4 and 2 here, which is the purple and green, there's a bit of overlap there, as well as class 0 and class 1 here. You can see that they have a sort of strange location. So those might be a bit difficult for the classifiers, but generally I think each of the classes are fairly distinct. On to feature selection and scaling. So for feature selection, we had to select 2 options, right? And I chose to do select percentile 90%, and I wanted to test how it would perform without doing that step. So those are my 2 options. I went with the 90% for select percentile, which is a pretty conservative amount, because I think PCA is going to consolidate any further similar fields. So I didn't want to go overboard on the feature selection and remove potentially useful features. And to test the select percentile method, I kind of followed the example in the books and the lectures where we added some noise columns. So I added 100 noise columns and tested to see how well select percentile did those columns. So we can see here that anything after 512 and onward was the noise columns. And we selected pretty much all of those features as well as a few additional ones. So I think this 90% thing will work fairly well. And I also want to talk about my scaling options. So the 2 options I chose for scaling were standard scaling and no scaling. Okay, so this next slide is a bit much, but this is how I'm organizing all of my tests. So we start with the raw data, right? And then we have our 2 feature select options. And then from there, we have our 2 scaling options, right? So now we've gone to 4 different combinations. And then we also have to have 2 PCA combinations. So that goes from 4 down to 8 different combinations. So I've shorthanded these to combination 1, 2, all the way to 8 within my report, just to quickly differentiate the different options I've had for the pre-processing steps. And from each of these combinations, I'm going to test 6 different algorithms. That's gradient boost, SVM, k-nearest neighbors, MLP, and stacking, as well as ADA boost. And so I'm going to be doing that for each of these combinations. So a lot of tests to run. Okay, on to my methodology for PCA. So we want to consider 2 different options, right? And I want to keep it at 90% of explained variance and 80% of explained variance. The issue with doing that is these variance thresholds are going to be different for each of the pre-processing steps that have been chosen. So, 80% here, that's going to be a different number of components than 80% for over here, where we've not done any feature selection or scaling, right? So that requires me to run some tests and calculate how many components it is for each of these 8 different PCA options, which I have listed out here. So figure 5.1, this is where I'm having feature selection and I'm scaling the data. And we can see that at the 80 and 90% thresholds, the 80% falls at about 104 components and the 90% is about 166 components. So that's what these graphs are showing. Yeah. So we can get into the results of some of the preliminary tests then, now that we've explained all the steps so far. So let's see, for gradient boost, the parameters I'm testing were max features, number of estimators, maximum number of leaf nodes, and the minimum samples per leaf. And my table here, figure 6.1, is showing the best combinations of parameters per metric and per pre-processing combinations, right? So combination 1 here, remember, that is using select percentile, standard scalar, and PCA at 80%. The best combination of parameters for accuracy was with log base 2, number of features, 750 estimators, 500 leaf nodes, and 10 samples per leaf at a minimum. Whereas the parameters that resulted in the best ROC AUC metric were these, and same for F1, right? So that's my logic behind this graph. And the gold cells are those with the most optimal metrics, which I have displayed here. These are the metrics for each of these best params, right? And so here I'm able to select the best parameters. That's how I'm operating here. And it seems that combination 6 was best for a gradient boost. So combination 6 was no feature selection, standard scaling, and PCA at 90%. And some, early estimations from these results, I'm going to further tune the models after this, after selecting the pre-processing steps. But it's apparent that I think overfitting is a bit of an issue here, just because the train and validation accuracy have diverged so much, as well as the train and validation F1 scores. And I also plan to tune the learning rate as well in future tests. Okay, on to SVM tests. So for the SVM, I selected, or the parameters I'm testing are C and gamma, and these are all the different values that I chose, anything from 0.001 to 100. And for SVM, I found that combination 4 led to the best metrics, so select percentile, no scaling, and PCA 90%. It was pretty obvious that combination 4 should be chosen for this one because it outperformed on all metrics. And I think there's some evidence of overfitting here as well, but it's not as bad as gradient boost. So we'll have to address that when we tune the parameters a bit further. On to k nearest neighbors. I tested the number of neighbors and the metric for calculating the distance between them. And here I selected, I believe that combination 8 led to the best results in general, you know. So combination 8 is with no feature selection and no scaling, and the PCA is at 90%. So the parameters here, they're already quite close. I don't think tuning the parameters much more will give us much better performance. So this is likely how it's going to perform in the final model. Is something to keep in mind. Okay, on to multi-layer perceptron. This one I tested different numbers of layers as well as different numbers of nodes. And you can combine these, right, to different combinations. So that's a total of 9 different combinations of layers and nodes between these 6 options. And I also tuned alpha as well. Or I tested for alpha, rather. And here, also combination 8 seems to be the best option. And it's looking, just some preliminary results indicate that there's not a whole lot of overfitting going on here, but we could squeeze a bit more performance out of it, likely. Okay, and on to Ada Boost. So this one, I tested the number of estimators and the learning rate, and I kept Ada Boost at just a decision tree. The estimator was decision tree where the max depth was 1, which I think is the default. So, and this one, I found that combination 5 led to the best results, which is no feature selection, some standard scaling, and PCA at 80%. So, Ada Boost surprisingly led to lower performance. I was expecting a bit better, but we can tune it to see if it improves any. Okay, this is going to conclude my preliminary results for Project 1. The next steps that I plan to do is I'm going to finely tune all the models now that I've selected for the best combination of pre-processing steps. And that's these 5 models. I also have not gotten around to exploring the stacking algorithm because I was waiting for some example code to come out to show how to best write that and perform those tests, which I think that was released today. So we can hop on that soon. And lastly, we want to analyze any misclassified samples between all of the algorithms before we choose what's best for this classification problem. All right. That concludes part 1 of Project 1. Thank you for listening.